A very nice greeting and good day wishes to all of you, my ordinary level candidates, and all students offering physics. I want to say, don't lose heart. Let us keep studying together. Today I'm going to look at a very prominent topic as we start on this topic. This topic is called moments. It is prominent, and incidentally, most students actually find it a little difficult from my experience as a senior teacher. Now, moments can be looked at as the turning effect of force, and I will give summarized applications. The turning effect of force, as you will notice, is applied on a day-to-day basis. If I may start with this, the applications are seen in the following. They are seen in the following. To mention the opening and closing of doors, and closing of doors and windows. I'm talking about opening and closing, not locking, but even locking with a key. The opening of taps, water taps. The tightening of nuts using spanners. We can talk about the opening. Where I talk about opening, you can always talk closing of jerry can covers. Jerry can covers are all applications of the turning effect of force. We can talk about the steering of the car, but that would appropriately come when we talk about couples. Now, what we need to talk about here that is again very prominent is what we call moment of a force. They can ask you to define moment of a force. Moment of a force. And this is usually about a point. About a point. The moment of a force about a point is defined as the product of the force. This is the product of the force and its perpendicular distance of the line of the action of the force, of the line of action of the force from the pivot, or otherwise referred to as the fixed point. We can illustrate this using a simple diagram. Illustration can be done using a simple diagram. Consider, for example, a beam, and consider a force F acting at 90 degrees, but from a point that is fixed, say point O. The moment of this force we are calling F. The moment of F about point O is obtained by saying it is equal to F times the perpendicular distance, which is x. And this gives us Fx, and it is supposed to be in Newton meters. And therefore, we can say that the SI unit the SI unit of moment of force, the SI unit of moment of force is a Newton meter, is a Newton meter, written as a Newton meter. And from what we see, it presupposes that moment of force is actually the same as work done by a force. It is the same as work done by a force. We can say, if we looked at a numerical example, now that we know what moment of force is, assume that I have a force of 4 newtons. I have a force of 4 newtons and it is fixed at a distance of 3 meters from a fixed point O. We can say that the moment of the 4 Newton force about point O is going to be equal to the force times the perpendicular distance, about that point, which will be 4 times 3, and we are saying this will give us 12 Newton meter. It will give us 12 Newton meter. That would be one good example. We can talk about the moment of a force. Now, the other concept we need to talk about now are conditions for equilibrium. We can talk about the law of moments. The law of moments is another common question. It is sometimes referred to as the principle of moments. Very common statement. Question is, state the principle of moments. I have called it the law of moments so that if they change the name in an exam, you should be able to get it right. We say that this states that for a rigid body, in equilibrium, the sum of clockwise moments about a fixed point is equal to the sum of anti-clockwise moments about the same point. I am going to emphasize this by illustration, that if we have again a beam whose knife edge or center of gravity is O, and this beam has two forces, say F1, acting at a distance x from that balanced point, and another force, say F2, acting at a distance y from the center of gravity. Then this force F1 will exert an anti-clockwise force and F2 will exert a clockwise force. So in equilibrium of the figure I have just drawn, it implies that the clockwise moments will be equal to the anti-clockwise moments, implying that therefore the clockwise moments which are moving that side will be the F2 times the perpendicular distance that I've called y, and we can say this is equation 1. The anti-clockwise moments will be F1 times the perpendicular distance that was called x, and this can be the second condition. So in equilibrium, we are saying it implies that if 1 is equal to 2, then this condition will always tell us that F1x will always be equal to F2x. This is the law of moments, but it is also a condition, as we shall shortly see. We can look at conditions for equilibrium, therefore. Conditions for equilibrium. Conditions for equilibrium of a body. There are two conditions for equilibrium. One is that the sum of upward forces, the sum of upward forces is equal to the sum of downward forces. The sum of downward forces. And again, for purposes of understanding, I will illustrate that if I have a body and I have forces acting on this body, and I also have reactions, say R1, and another reaction here, say R2, we are saying that if there is another force here, F1, F2, and these distances can be X, these distances can be known. This can be Y from here to there, and this can be Z. So for this condition, it implies that R1 plus R2 are upward forces, and F1 plus F2 are downward forces, and therefore the statement is that R1 plus R2 will always be equal to F1 plus F2 in equilibrium. Will always be equal to F1 plus F2 in equilibrium. That is the summary of this condition. That is the summary of this condition. We are going to look at the second condition. We are going to look at